Hi, everyone. This is Mrs. O'Reilly, Miss Ashburn, and Mr. Harfiness, and we're here to talk about radiation and half-life.
Am I up?
Yeah, we never
Okay.
really finished planning.
That's all right. I can go. Hi, guys. So really what we're doing is bringing back from the beginning of the year, just reminding you some of the basics before we talk about the nucleus and its energy. So you don't forget you have the protons. They're in the nucleus. They've got the positive charge, right? And they're the atomic number. That's how we figure out how many protons an element is, and it identifies the element. Then there are the neutrons. They are also in the nucleus. They have no charge. They're actually the glue. They're like the glue that keeps the nucleus together, that allows all those plus protons to hang out there. Protons and neutrons both have an atomic mass of 1 AMU. Remember, it's relative, so they're about the same size, so they get a value of 1. And then you have those electrons. They're still there, even if they're not the focus so much of this unit. The electrons are still outside the nucleus. They've got the negative charge, and they've really been the ones we've been talking about up to this point that kind of cause all the reactivity, why elements are where they are on the periodic table. But now for this unit, we're going to be really focusing on the nucleus. We talk about the energy that it takes to hold it together and what happens when it has a hard time holding it together. And just a reminder, because we're going to be talking about isotopes, that the mass number, not the atomic number, but the mass number is protons plus neutrons.
Okay, so Ms. Ashburn led right to what is an isotope. So remember, the definition is going to be that it's going to be an atom that has the same number of protons, but a different number of neutrons. So what eventually happens is that because of the different number of neutrons, the atomic mass is going to be different. I think you're looking at this picture of boron, and you can see here that it has 5 protons, 5 neutrons, and 5 electrons. Remember, as Ms. Ashburn said, the protons plus the neutrons is going to give us the atomic mass. So there was 5 protons and 5 neutrons that gave us 10. An isotope of boron is on the right. You're going to see that it has 5 protons and 6 neutrons, this time giving us a mass of 11. Now, these two isotopes are stable. What we're going to be talking about throughout the course of this unit is what happens if the isotope is unstable.
So when an isotope is unstable, it's called a radioisotope because it's radioactive. They can also, I have to move my pictures. They can also be defined as atoms that have an unstable combination of neutrons and protons. They have excess energy inside of their nucleus. So a couple examples are hydrogen-3, which is called tritium, carbon-14, chlorine-36, and lead-210. Remember, again, that it's written as the element name, then the dash, and then the mass number, and that mass number is the protons plus the neutrons.
All right, so next we're talking about what radioactive decay is. And remember, Mrs. O'Reilly talked about how radioisotopes are unstable. So the nucleus has a hard time kind of keeping itself together. So radioactive decay is what happens when it can't keep itself together. So radioactive decay is really the spontaneous breakdown, which just means it happens whenever. You don't necessarily have to cause it to happen. It will just happen because it can't hold itself together. And so what you're going to get is a release of particles and or energy from the nucleus when it decays. So you're going to see here, right, there's the nucleus. All right, and here it's just showing 3 different types of emissions, meaning things leaving the nucleus when it decays. This is called an alpha particle, this is called a beta particle, and this is energy, the gamma ray. All right, so they have unstable nuclei that can't really keep it together, and so pieces and energy are going to come apart. And there you go.
So now we're going to talk about how fast they decay. Now, it's kind of a loaded question because it can be really, really quick, less than a second, or it could actually be billions of years. Okay, each isotope has what they call a half-life. And what the term half-life means, it's going to be the amount of time it takes for 1/2 of the atoms of a radioactive material to disintegrate. So if you look at the graph, I think the graph actually speaks a lot better than words here. You can see that originally you started with, they're using percentage. So let's just pretend those were atoms. So let's say we start with 100 atoms. And over the course of one half-life, you're going to notice that it goes from 100 atoms to 50 atoms. And then as you go another half-life, it's going to go from 50 atoms to 25 atoms. And then after the next half-life, it's going to go to 12.5. And that process is going to repeat itself over and over and over again. So you'll actually never totally run out, but you're going to, but there's going to be a very, very, very trace amount left.
So a couple examples of radioisotopes and how long their half-lives are. First, we have hydrogen-3. It's 12.32 years. So every 12.32 years, the sample will decay in half. And that would be emission of particles or energy from the nucleus. This is a mild radiation. It's used for commercial, military, and different scientific endeavors. Pretty safe because it cannot penetrate the human skin. Another isotope that is used is carbon-14. Its half-life is 5,730 years. So in 5,730 years, half of the sample will decay. Another 5,730 years goes by again, half of that remaining sample decays, and it continues to cut in half each time. And this is used for radiocarbon dating. So fossils of a certain age, we can use carbon-14 dating to identify how old those fossils are.
Okay, so now we're talking about how you guys will be doing some half-life calculations. And you're gonna be looking at really just kind of from one point of view. So here the example we use to kind of walk you through it. And when you do part B, the half-life simulation, you're gonna have a couple of these problems in there to practice. So here they're giving you iodine-131 as the radioactive isotope. It is often used in certain medical treatments. It has a short half-life of about 8 days. So the question is, if you had a 100 milligram sample, how much would be left after 24 days? All right, so you need the half-life, the initial sample size, and then total time. The fact that it's used as a medical treatment, while interesting, is not relevant to solving the half-life problems. So your first step is going to be to figure out, well, how many half-lives is it? All right, so you're going to take your total time, which is 24 days, right? You're going to divide it by the 8 days, and it's going to give you the 3 half-lives. All right, so that's the total number of half-lives. Then really all you're doing in step 2 is you're going to start with your initial sample and divide it by 2. That's going to give you 50 grams, or milligrams, which means there'll be 50 milligrams left after the first half-life. You take that 50, because that's your new sample, divide it by 2, and now you have 25 milligrams. So there would be 25 milligrams after the second half-life. Take that 25, divide it by 2 for the 12.5, which means after your third half-life, your sample now would be 12.5 milligrams. So you're going to have an initial amount, and you're going to keep dividing your sample size, right? So here's your new sample size, it's a 50. You're going to keep dividing it by 2 for the number of half-lives. So the answer to this question would be then 12.5 milligrams would be left. And here we've got a nice pictograph to kind of walk you through what that means. So here, the 100% is your 100 milligrams. Here's your 50 milligrams, your 25 milligrams, and your 12.5 milligrams, just to kind of give you the visual.
Okay, I'm going to go through this slide fairly quickly. There are 3 major ways of how we detect radiation. The first is a Geiger counter. Ms. O'Reilly is going to put the pointer over which picture it is. Okay, so you're looking at it in the top. First of all, as Ms. Ashburn mentioned before, there are 3 major types of radiation, alpha, beta, and gamma, which we're going to talk a little bit about next week. And this type of radiation detecting has been around for almost 100 years. The second type of I can't think of the words besides a screaming baby. The second type of counter is called a centellian counter and produces a bright flash of light. And they're a little bit more precise than Geiger counters. And then finally, we have what is called the film badge, and that's when radiation passes through one of several filters or through a transparent area before striking a film. Okay, they are used to monitor your degree of exposure, but they don't protect you from exposure.
So there's 4 different ways that we use radiation. We use it to analyze matter. We use it as tracers, to diagnose medical problems, and to treat diseases. And we have some information about each of these in the coming slides.
All right, so I'm going to talk about analyzing matter, and the first thing is the neutron activation analysis. So what this does is it detects trace amounts of elements in samples. So you have a sample that's bombarded with neutrons from a radioactive source. So some atoms will become radioactive, and then half-life and type of radiation emitted can be detected and analyzed by the computer. So it's used in museums to detect art forgeries, and in crime labs to analyze gunpowder residue.
Okay, I think it's my slide. Using tracers. Okay, so tracers are going to be used in agriculture to test the effects of many different herbicides and pesticides and fertilizers. Okay, so the tracer is first introduced into the substance being tested, and then plants are treated with the tagged substance. I think if you look at the picture, you can kind of see what's happening there. Okay, and you can kind of see where the radiation is in the plant. Then devices that detect the radioactivity are going to be used to locate it in the plant. And then finally, sorry, I can't talk. Tracer can be monitored in animals that consume the plants in the water and soil. So I guess the long way of saying this is that if we, an animal or a human, is able to eat some of these plants, we would still be able to find the tracer in us. I'm going to pass it over.
There you go.
The next is for diagnosing medical problems. So the example to the right shows how iodine-131 is used to detect thyroid disorders. Your thyroid is located in your neck. It controls the rate at which your cells release energy from food. Patients will drink a drink with a small amount of iodine-131 in it. And then after about 2 hours, that amount of iodine uptake is measured with a radiation detector. And then you can kind of use it to diagnose or detect any medical problems. Other things that are, isotopes that are used are technetium-99m, used to detect brain tumors and liver disorders, and phosphorus-32, which can detect skin cancer.
Okay. All right, my turn. Sorry, had to remind people I was filming. So treating diseases, there are radiation is going to be used in different types of diseases. Some that you actually are familiar with, others you may not. So it is used to treat some forms of cancer. You have the high energy radiation, which is the gamma rays. They are going after the fast growing cancer cells. The problem is they also do go after some of your healthy growing fast cells, because your body is made up of fast cells. So a lot of the side effects you know about from chemotherapy and radiation come from that. And so you basically are going to be balancing the two things. Also, in terms of seeding, so salts of radioisotopes can be sealed in gold tubes and inserted into tumors. They emit beta and gamma to kill the surrounding cancer cells. And then some prescription medicines, you have gold, iodine, and phosphorus. So for example, iodine-131 in large doses is digested, then carried into the blood to the thyroid, where it emits beta and gamma radiation.
Okay, and to end for this week, that is going to be our lesson. There are going to be 2 additional parts or tasks for you to do. And as always, if you have any questions, concerns, or comments, please let us know via Google Classroom or email. And we will see you soon. Bye.
Bye, have a good week.
Oh, I should stop recording.